Morning. So I'm going to just review my first year of fieldwork that I've done on nitrous oxide and methane from peatlands undergoing land use change on Sumatra. Ooh, next. Okay, so I'm just going to set the scene, a little bit of background on the changes that occur between intact forest to palm oil, talk about my results so far, attempt a little discussion about those results, and then review what I'm going to be doing for the next 2 years of the Ph.D. This is just some of the guys we work with in the palm oil, keep them wrapped up in plastic. Okay, next. Okay, so as Christelle said, I'm looking at how land use change affects gas fluxes on deep peat in Jambi. Now, what I'm going to talk about today is just two aspects of the field work that I've been doing. I've been taking monthly samples for a year, and I've also done a fertiliser application and got some quite interesting data from that. So a long-term study and a nice shorter-term study. Okay, so just introduce my gases. Trace gases, methane. Even though they're released in a smaller amount than CO2, they're actually potentially have a higher ability to store infrared radiation, therefore leading to global warming. Methane, the reason it's highlighted as a greenhouse gas is it can enter the troposphere and it can cause chemical interactions that can lead to ozone depletion, breakdown. For my purposes, it comes from a variety of sources, but in peat, I'm looking at the top surface and how it's formed during decomposition of organic matter. Okay, nitrous oxide. Again, it's released in much smaller amounts than CO2, but it's actually 300 times has the capacity to hold on to the sun's infrared radiation. It also contributes to breakdown of ozone. It's a product of microbial origin, so looking in the peat, I'm trying to understand these processes that are leading to the release of nitrous oxide. In recent years, the balance has been disturbed a lot by human activity. Now that's what I want to understand more with this change from intact forest to palm oil. Basically, the disturbance leads to inert forms of nitrogen in the soil being basically liberated, freed up into the atmosphere. Okay, so where am I? So we are currently working in Jambi. So we have our peatlands here, and I'll just zoom into a slightly better map. So Jambi province, we live here, and then we've got peatlands across here. The red is a palm oil plantation, and the blue star is the intact forest. So you can see they're on the same. You can see they're on the same area of peat. It's good for our comparison. Okay, so I'll just introduce you to the three sites that I'm looking at. This is my intact forest at Burback. As you can see here, it's waterlogged. It's a natural peat swamp forest. We've got a really nice variety of species of plants. The water table doesn't tend to change that much through the year, but in the summer it does fall slightly, well, in the dry season. The peat is about 4 meters deep on the site that I'm working on. Okay, transition, logged forest. Now, to put this into context, this is a site that we're looking at now. Previously, this was intact forest. It's been, the process of change has already been started, but they're not actually undergoing change at the moment. So what it is, it's a transition site. The primary forest has been felled and taken away, and now we have secondary forest that's taken over. However, it has been drained. We've got a low species diversity, so we're not looking at the waterlogged conditions of Burback, and we're not looking at the palm oil total one species, basically. The peat here is very deep, it's 7 metres. Okay, so final stages. We've got the palm oil. As you can see, it's dramatically different. The water table is permanently lowered. The palms that I'm looking at here, they're 7 years old. The peat's about 4 metres deep. Now, as you can see, we have loads of bare peat. There's no waterlogging. This landscape is very different to how it would have been. Okay, so I'm just going to quickly talk through the stages that they go through to convert primary forest to this palm oil. Okay, so they install the drainage canals. They basically build up levees or bunds, that they call them, and it's just like piles of earth to try and control the flow of water. They take away the decent trees that they can make some money from. Sometimes they burn the land, sometimes they don't. It depends on the land management strategy of the particular company that's gone in. They windrow the biomass. What this means is every other row, they will just take any sort of leftover organic matter or leaves and twigs and things and just put them into a row. The peat is compacted. Now, this comes in two ways. The peat's compacted because of all this human activity on the land. It's always going to happen. But also, they bring in earth movers, like tractors and things, to actually try and compact the surface of the peat a little bit. Then, final stage, obviously, is the planting of the palm oil. Okay, so how do these changes actually affect the peat? Why am I going through this? So we're going from a waterlogged situation to a drain situation. So anaerobic conditions. This is anaerobic decomposition of matter that leads to production of methane. We change to a drained situation. So oxidation can increase. Nitrous oxide can be formed. Peat swamps tend to be quite nutrient poor. So in the oil palm, what they do is they have to add trace elements, fertilizers to boost their yields. How efficient this is, there's studies undergoing at the moment to try and find out if these methods are effective. In your peat swamp, you've got peat that's accumulating over time. It's in a nice balance. It's a carbon pool. In the oil palm, peat's compacted. We're losing material over time. It's carbon loss and also nitrogen loss. Okay, so we're going from low bulk density with high pore space. Basically, what this means is it enables nutrients in this situation to be able to cycle more efficiently through the system and are available to plants. So even though it's nutrient poor, they're making use of what they've got. In the oil palm, the soil is dramatically changed. The nutrients can be more prone to leaching because they're not actually held in the pore spaces of the peat for so long. This can cause not just in situ effects, we can also lose our nutrients to the surrounding landscape. Okay, so I'm going to talk about my work now. I've got 3 plots that I've just talked about. On my plots, I've got 10 collars per site, and I'm also using some floating chambers. A piezometer is with each collar. Now, this is just to look at the water table level. Each time I go, I take soil and water samples. I take general environmental conditions, air and soil temperature. We have a weather station installed for each site, which records rainfall hourly on a data logger. When I take my gas samples, I take from 0 to 30 minutes. So my 0 is the current atmospheric conditions, and then I can see how the gas fluxes increase over half an hour. Okay, there's a little shot of one of my chambers, and then we've got the gas bars that I used to take them away. Okay, so now I'm just going to talk about my first year of results, just monthly. Okay, so first of all, this is the logged forest, nitrous oxide fluxes. So I started taking gas samples in October last year, and we're going through to, I think, up to July, sorry. Okay, so we've got this next in is burback. So locked forest and burback for nitrous oxide, it's relatively low. Burback is my intact forest. So the oxidation is low, it's a waterlogged forest. This is kind of what I would expect to be finding there. And here's my oil palm. As you can see, it's higher. It's slightly higher through the year now. I've got some data that sort of sits in. Now I'm still looking at this, but I'm thinking that the reason I've got quite low fluxes of nitrogen here is because of heavy rainfall just before I took my samples. When I take my gas samples, I take them the same time every day. So if it rains, this can affect my results. Now methane, same order again. Logged forest, low methane. It's drained, so there's no anaerobic conditions there. Burback, it's waterlogged. I've got a dramatically higher methane release. Here, when I went, it hadn't rained. It was quite unusual. This is, let's have a look. This is sort of December, November time, and unusually in Burback in the wet season, it was actually quite dry. So in the few days leading up to it, now whether this led to lower methane emissions. And finally, palm oil. There's high oxidation here, it's very dry, so my methane emissions are low. Okay, so I'm just going to talk about my short-term study. What I did was I wanted to add fertilizer, ammonium nitrate, to my palms to find out if these are affecting gas emissions. So in the oil palm, they tend to add potash, ammonium nitrate, which is the study that I did, and also phosphate. So I treated 5 of my palms with 0.5 kilogram of ammonium nitrate. I just followed the procedures that they would in the plantation. I didn't really change any methods. I just did what they do. Now, for the purposes of these results, I've divided my graphs into the fertilised zone and the non-fertilised zone. So I'm just going to show you a picture to sort of make that a bit more clear. So here we've got one of my palms. Now, if you can see around the bottom, there's sort of like a circle of bare soil. Now this is the root zone. So what they will do in the plantation is they will literally just put the fertilizer onto the surface of the soil and leave it. There's not really much science involved with it. It's just a circle about 1.5 meters diameter around the palm. So fertilized zone near to the tree, and my non-fertilized zone sat out here. Okay, results. So first of all, I'll go through the nitrous oxide fluxes following this. Okay, fertilized zone first of all. This was the day before I applied my fertilizer. I applied my fertilizer on the second day, and then these are intermittent results following that. Non-fertilized zone. I've got higher nitrous oxide emissions from the non-fertilized zone. I must admit, I didn't expect to see that. So I'm currently having a look and thinking about why this is happening. I need to think about this. So there's a few ideas that I've got at the moment. I applied my fertilizer here. Really, really heavy rain. It was tremendously heavy rain straight after I applied. The top surface of the peat is so dry and baked, I don't know whether there's a runoff to the non-fertilized zone, because I don't know if you noticed with the palm, it sort of sits above and then it goes down into the path. Could this have just simply run off down onto the path? Okay, now methane. Fertilised zone methane. It's sporadic, but it follows a pattern of rainfall actually. I'm afraid I haven't got the data to show you, but it follows, basically I applied my fertiliser here. You know when I mentioned I had that really heavy rain? Here and here. So whether this, the soil processes are enabling this to be produced. Okay, so methane from the non-fertilised zone is opposite. So I'm currently looking at these and wondering what's going on really with this. As I say, I have a few ideas whether runoff is affecting it or, yeah, I'm quite baffled by this at the moment, so I need to look into that more. Okay, so what next? Lots. I want to characterise my, my data collection more. I mentioned that I only take my samples at one point in the day. This concerns me quite a lot because I want to find out what's going on over a 24-hour period. So I can say that my gas fluxes are actually representative of a 24-hour period. So what I've done is I've done one day of 24-hour sampling, and I want to do that again just so I can have a look at what's going on, whether rainfall does actually affect my gas fluxes. I need to look at the controls also. We've got known controls on gas fluxes, soil moisture, water table, things like that. I need to be looking at that more. I'm going to repeat my fertiliser application in the wet season only, so that will be next year. Lab work, I want to do some work with the peat, wetting and re-wetting, having a look at how these physical changes can affect gas fluxes, and also looking at mineralisation in the peat. Then, way in the future, into the last part of the PhD, I'm going to input to models. So when I've got a really good data set, I want to input to some models, and I can upscale then and possibly make predictions for the future for the gas fluxes. And that's the end. So thank you.